Now we consider refraction of light. Already we finished reflection. Now we consider refraction. In that we take Snell's law. The statement is this: the ratio of sine of angle of incidence to sine of angle of refraction is constant for the given pair of media and is equal to the reciprocal ratio of refractive indices. That means sin I by sin R, ratio of sine of angle of incidence to sine of angle of refraction. This is equal to the reciprocal ratio of refractive indices, mu2 by mu1. Mu2 refractive index of the second medium, refractive index of the first medium, both with respect to free space or air. Or you can even say mu1 sin I equal to mu2 sin R. This is Snell's law. We have to prove this Snell's law using wave picture or using wave theory. Consider the diagram. Here we consider the first case in which light is incident on a denser medium. That means light travels from rarer medium to denser medium. A rarer medium is one whose refractive index is less. A denser medium is one whose refractive index is more. These are optically rarer and optically denser medium. Okay, so look at this diagram. This is the diagram giving both rays and wavefronts. These two are incident rays. You see they carry arrow, and this is the incident wavefront. This is 90 degree. Always a ray will be perpendicular to the wavefront. Okay, if this is I, this is also I, and this is R, angle of refraction. Angle of refraction, not reflection, okay, because the phenomenon itself is refraction only. Now we have to construct the refracted wavefront. What we should do? We should assume here that time taken that is by the time the point B reaches C, then the point A reaches E, and the velocities are different, V1 and V2. Velocity in the first medium V1, second medium velocity V2. By the time B reaches C, A reaches E, because this is now incident wavefront AB. This wavefront only travels like this, okay, and comes like this. So AB now at a later instant of time CE. Okay, but how to construct CE? We will have to use Huygens principle. Let's say T is the time taken for the wave to go from B to C, and then instead of T we can even use tau. Okay, let's say we can even use tau, right? Tau is the time taken for the point B to go to C. Now taking A as center, V2 tau as radius, you will have to construct a sphere or circle, sphere in 3D, circle in 2D, but full circle not necessary. Moreover, we are going to consider the wavefront, the wavelet in the forward direction. So you just to draw an arc whose radius is V2 tau. It will represent distance. Velocity into time is distance. Just to draw an arc, then draw the tangent from C to that arc. So CE will be refracted wavefront. Tangent is drawn from C to the arc, as I have shown here, on the refracted ray or this line AE. You can even just say, imagine you can draw a bigger line, and then in that you cut the arc. Okay, so and then draw tangent to the arc. That's how you get CE as a refracted wavefront. Okay, then this distance BC is V1 into tau, distance AE is V2 into tau, because the velocities are V1 and V2. Now sin I So in triangle ABC, in right triangle ABC, sin I opposite by hypotenuse, BC by AC. Also in triangle AEC, you get sin R opposite by hypotenuse, AE by AC. Therefore sin I by sin R is equal to BC by AC into AC by AE. Okay, you can cancel this AC. Okay, I just change the color. AC you can cancel. Okay, now you have BC by AE. So sin I by sin R is equal to BC by AE. This is AE. BC V1 tau. AE here V2 tau. Tau of course you can cancel. So you get V1 by V2. So for the given pair of media, V1 by V2 is constant, so don't forget it. So we can say sin I by sin R is constant. Okay, you just keep it like that. Sin I by sin R is velocity in the first medium divided by velocity in the second medium. Now what do? You consider this situation in which first medium is air or free space. The second medium is this medium 1. I just make this to be medium 1. This medium 1, suppose if this is water, this will be water. If this is glass, two cases, air and glass. Okay, so these are two different diagrams, so don't get confused. Two different diagrams. Now what happens, very interesting, this is air, this is medium 1. If this medium 1 is say water, this is water. Medium 2 is glass, let's say this is glass. If, okay, now consider diagram 1, and that refractive index of this medium with respect to air. So mu1, actually it is A mu1, so generally we don't write that A, so mu1 is C by V1. How? Ratio of speeds is refractive index. Okay, then considering diagram 2, mu2 is equal to C by V2. Here speed is V1, speed is V2. These two are refractive indices. Now you call this as equation 1. Okay, from this you get V1 is equal to C by mu1. From this you get V2 is equal to C by mu2. So substituting this and this in equation 1, you get sin I by sin R is equal to V1 by V2, no, from equation 1, right? So V1 by V2, C by mu1 for V1, for V2 C by mu2, but you are dividing mu2 by C, cancel out this CC, you will get mu2 by mu1. Sin I by sin R, mu2 by mu1. ratio of sine of angle of incidence to angle of incidence to sine of angle of refraction is equal to the reciprocal ratio of refractive indices, you see here, right? Now you can even write this as mu1 sin I is equal to mu2 sin R. Okay, this is called as Snell's law. Called as Snell's law, right? Now you can even get one important concept clarified here. What is it? Suppose if you consider this, okay, that is, I just write here sin I by sin R same thing I am writing. This one I am writing it here. Sin I by sin R is mu2 by mu1. So if you assume mu2 greater than mu1, because this is denser medium, if you consider this medium as denser, then mu2 should be greater than mu1 by definition. So sin I greater than sin R, so I greater than R. Come to this picture, I greater than R, which indicates the ray bends towards normal, bends towards normal. Also, one more thing, sin I by sin R, you get mu2 greater than mu1. Mu2 greater than mu1 here will be V1 greater than V2. Also, V1 is greater than V2. That is, speed in the first medium is greater than speed in the second medium. That means in a denser medium, speed is less. That is the conclusion. Speed of light is less in a denser medium. Is less in denser medium. Why? Mu2 is greater in a denser medium, so V1 should be greater. V1 is speed in the first medium. Speed in the first medium is greater, second medium is lesser, second medium is denser, so speed of light is less in the denser medium. So by simple proof, you also get the idea that the ray bends towards a normal. Also in a denser medium, speed of light is less. This is contrary to the prediction of corpuscular theory. Corpuscular theory says that speed of light in a denser medium is more, but that is not correct. It was experimentally proved that in the denser medium, speed of light should be less. That here also we get the same thing. Speed of light is less in denser medium.